Welcome to our unit's Lesson 2 on thermochemical changes, focusing on calorimetry, a method to measure energy changes during chemical reactions. We will learn how to quantify this energy transfer using mass, temperature change, and specific heat capacity. Energy, though not visible, can be measured through its effects, with calorimetry allowing us to observe these changes in a lab setting.
Thermochemistry is the study of energy changes that occur within a chemical system during a chemical reaction. Calorimetry is the experimental technique used to measure those energy changes. This is done using a device called a calorimeter, which is designed to isolate the system so energy changes can be tracked accurately. The basic coffee cup calorimeter, made of a polystyrene cup and lid, uses a thermometer to detect temperature shifts during reactions in the known volume of water inside. A bomb calorimeter measures the energy released by combustion reactions in a sealed container by observing the resulting temperature change in the surrounding water. In calorimetry, it's assumed that the calorimeter absorbs all energy changes from the chemical system, that the system is isolated with no energy escaping, and all involved materials are conserved. We assume dilute solutions have the same specific heat capacity and density as water, and the calorimeter doesn't significantly absorb thermal energy. First, thermodynamics law states energy can transform but can't be created or destroyed. Second law indicates energy moves from high to low energy areas. These laws clarify heat transfer in chemical reactions. Thermal energy is the total particle kinetic energy in a substance. Heat is energy transferred due to temperature differences. Transferred heat quantity depends on mass, specific heat capacity, and temperature change, and is measured in joules. Specific heat capacity measures the energy needed to increase a gram of a substance's temperature by 1 degree Celsius. Calorimetry utilizes the water's temperature shift to ascertain the energy exchange in chemical systems.
In this example, we determine the change in thermal energy when water is heated. We begin by identifying the mass of the water, calculating the temperature change, and applying the calorimetry equation. Press pause and try it yourself. The solution to the problem is here. How did you do?
Temperature reflects the average kinetic energy of particles such as electrons, vibrating atoms in bonds, and molecules. If the temperature changes, it means kinetic energy has also changed. Potential energy, in chemistry, refers to energy stored in covalent, ionic, and intermolecular bonds like hydrogen bonding. Changes in these bonds alter potential energy. Enthalpy, the sum of a system's kinetic and potential energy, can't be directly measured. Instead, we assess the surrounding temperature change under constant pressure to calculate the system's enthalpy change. In a chemical reaction, the system's potential energy loss equals the surrounding's kinetic energy gain.
In this example, a candle heats water. We use the measured temperature change of the water to calculate the energy released by the chemical reaction occurring in the candle. Again, press pause and try it yourself. Here is the solution. How did you do this time? In an exothermic reaction, the chemical system releases energy, and the enthalpy change is negative. The temperature of the water increases. In an endothermic reaction, the system absorbs energy and the enthalpy change is positive. The temperature of the water decreases. This example involves the neutralization of an acid and a base in a coffee cup calorimeter. We calculate the temperature change of the solution and determine the enthalpy change of the chemical system. Give it a shot. Press pause and see how you do. Did you calculate this correctly? If so, great. If not, perhaps a review is in order?
Molar enthalpy is the enthalpy change per mole of a substance, with the total change depending on the number of moles and the reaction's molar enthalpy.
The molar enthalpy of combustion denotes the energy released upon complete combustion of a mole of propane, enabling energy change calculations for any propane mass. This can be calculated by multiplying the number of propane moles by the molar enthalpy, yielding minus 504 kilojoules. In this example, we predict the enthalpy change resulting from the combustion of a known mass of butane using its molar enthalpy of combustion. Once again, press pause and see how you do. This one is really the same as the propane problem, just a different fuel. Did you get it right?
In a calorimeter, the enthalpy change of the chemical system equals the thermal energy change of the calorimeter. This relationship allows us to calculate enthalpy changes using temperature data.
Press pause and give this one a go. The lab experiment involved burning ethanol, using the resultant heat to warm a large volume of water. To reinforce today's lesson, read pages 485 to 493, complete the assigned practice questions, and section 11.2 review questions.